Not sure anyone needs it. I don't think Jeff needs introduction, but Jeff Newmark's going to talk about his SOPEX mission design study.
All right, thanks, Don. Okay, so this is a companion study. Don already presented a Pathfinder or a small sat version of this, where that could be standalone or mixed with a constellation, as Paulette said. That's a really interesting way of getting this done, where you can get full coverage. We heard from Les that, this hovering ability is probably not feasible in the near term. So some of our studies who want 6 months over one pole, how do you do that? Well, what Paulette showed and what Don showed a component of is you can do that very well if you had 3 or 4 of these. And I think Tom is going to be talking a little bit about that as well. This is the companion of that. This study, we decided, what do we do if we want to go larger? This is if we want to do kind of a single stereo spacecraft, but kind of more of that size spacecraft where you do put a pretty large complement of instruments and you kind of go for broke at that point. So what do you do? This is the flip side of that study that Don presented. I'm not going to discuss, we've been hearing for a day and a half all the wonders. One of the things I do want to stress is the part of the study that we decided to focus in on, while it's larger, we also said, what can we do with technology that is really at least TRL 5 today? No TRL 3, though I do want to fly Neil's stuff. That is way cool. I do want to fly that. Let's put that on a sounding rocket at least or something. Come on. I have a balloon going up next September. Give me one of those. But no, so this study said, what can we do with TRL 5? That was kind of our limit on this study, nothing crazier than that. And what can we do, and how big can we make this, and what kind of parameters can we use, and what kind of mission can we define from that? So, cut to the chase, you saw Don showed a version of this. With TRL 5 and a big spacecraft, we heard from Les, I'm not quite there yet with Sails, but I certainly am there with Jupiter. So this does go out to Jupiter, similar to the previous studies. Then I said, well, I'm also impatient. I don't have 6 years to wait in between each pole. So how do I get something that's a little bit more circular? And the answer was ion engines. Particularly next thrusters, next or around TRL. I think Les told me he may have been funding the first person at NASA to fund those in 2003. They've been under development for a long time. They've actually, I think, been selected in the Phase A studies for New Frontiers now in the Caesar mission. It's going to a comet, I think, that has next thrusters. But they're around TRL 5. They haven't quite flown yet. They may even be TRL 6, but they are real. They're real. I mean, these are not pie in the sky future ion, future SEP thrusters. These are real thrusters. They take power. You need about 8 kilowatts. So you need some arrays, so you can do that. You have ROSA arrays. They're flying plenty of big arrays. Juno has giant arrays right now. So that allows you to circularize. This is a mission. You see here in 10 years. I can get 3 passes from 10 years from launch date. This is so 10 years from the day of launch. This mission can achieve 3 passes over each poles. Each pass, again, exactly as Don explained, it depends on exactly where you want to define a pole. Is it 60 degrees, 70 degrees? But it's a very similar orbit to what Don showed. So it's about a little over 2 months over 60 degrees, around 3 months over 50-something degrees. It's a similar type of time over the poles. So this is, starts to become quite exciting. 10 years, 3 passes. That's a lot of data coming down. Some of the characteristics. This is a bigger mission, as you see. This is not a small sat. This is not intended to be a small sat. This is saying, hey, what if we want to go for broke? What do we get? So I'm up to, I said maybe even a little bit heavier than stereo, but of that order of stereo size, not quite an SDO size, but a sort of a decent size. Needed a little bit bigger rocket to do this. You need the C3. Cannot be done on a Falcon 9. So Atlas 5 though does it fine. Delta 4 Heavy would do great. Falcon 9 Heavy would do great. Or maybe we could talk about whether you could do something with an upper stage instead of a Falcon 9. That's a little bit on the edge. I would have to go a little bit lighter to quite get with that, with an upper stage. Again, need the 2 next thrusters to do this. It's kind of interesting. The thrusters burn during perihelion, so when it says you can take data except for the thrusters burn, you're probably not going to be taking data at perihelion, so maybe you miss some low latitude. This particular orbit assumed I stopped taking data below 50 degrees. And I fired my thrusters for the entire time from 50 to minus 50 or minus 50 to 50, and that allowed you to circularize it. You can play, that's a parameter. You can decide how many days you want to fire your thrusters or how many thrusters you have. You can add more thrusters, you can thrust less time to change your orbit. And again, this, one thing I forgot to mention in this orbit, I did go into the half an AU. This is a final, this ends at the final orbit of just a little over a year period. And it's a half a AU by 1.5 AU is at the 3rd time. You can, mission keeps on going. You can continue to circularize wherever you want, whatever you want to get to. If you want to go out to, if you don't want to go quite into a half an AU, it's not quite as effective. I mean, the thrusting at perihelion is most effective the closer you're in. If you step it out to 0.7, your orbit gets extended a little bit longer, or you need more orbits to get the same. So that's kind of how it works. Kind of how it works in the physics. So you always want to keep this stuff in mind. These are all trades that one can do for a real mission, but these are trades that you do have to do when you actually design a real mission. You can't just say, "Oh, I'm going to go to 90 degrees," because that may not be possible with an existing rocket. With an existing mass payload, you might have to settle for 75 degrees, and these are all part of that trade space. Let's see. So some other details of this, and again, this was an actual design study for a real mission. What could we do? I had 8 to 10 kilowatts of solar array size. One of the limiting factors is keeping yourself warm out at Jupiter. Actually, it's one of the things that is most difficult probably for these Jupiter Gravity Assist missions is the thermal range. So I have a factor of almost over 120 range of thermal input from a half an AU to 5.5 AU. So to keep yourself nice and, you don't want to be frozen out at Jupiter, so you need a lot of power, but you have no sun. So you need really big arrays. For the ion engines, of course, you need a range. So actually, they're about similar requirements. So this does do, if I have it about 10 to 15 kilowatts, 10 kilowatts, that works out quite well. Again, a range of rockets, but a Falcon 9 by itself won't do it for this mass payload. It just doesn't have enough C3, even with maybe with a Star 48, but Star 48 is what Solar Probe has as their upper stage. But that's still pushing it for something this size. Someone asked, I think I heard earlier about discussions. Maybe it was Bob who was asking about when can you do things. If you give an orbital dynamicist time to play, boy, they can find anything for you. So these are just some examples of you can whip by the Earth once around, you can hit Earth and Mars, it all depends on your exact launch date, to try and speed up things and try and get you set up right to go on your way out to Jupiter. And it's billiard balls. They just bounce you around the solar system and you get to where you want to go. It's all a matter of time. But the key is it's repeatable. This is an example. So it's really hard. This is a little bit of a confusogram plot, but here's on dates and here's possible launch dates and delivered mass to Jupiter. And you see there's quite a big range here. Now these are some big masses, by the way. These are over 1,000 kilograms, and I didn't have that. So you can, but you see here, it depends on when you go exactly how much. So this is why you just say, oh, can't you go to Jupiter and hit like Ulysses did? No, they had a very specific launch date. And you have to pick those very, very carefully. You can't just say, I'll launch any time and get 1,000 kilograms or 1,500 kilograms to Jupiter. You have to, you see the ranges here, but there is cyclical. You do hit a lot of times. And so you can get a launch, especially if I'm down at where I was at 750 kilogram. There is a number of times you can get, you said sometimes you hit Mars, sometimes you loop back and hit the Earth again. Sometimes you just go direct to Jupiter. It really just depends on the exact launch date. But this is all very feasible. I have not talked about any technology now. These arrays exist, the thrusters exist, the instruments I haven't got to yet, so let's talk a little bit about spacecraft and instruments. We studied 2 designs, actually, and these are, big surprise here, big, box design like we always do, or you can put it all on an Espagrandes if one wants to use Espagrandes. They sound really exciting. Oh, Moog selling them. I hope if there's any Moog people here, I don't mean to disparage them. They're great for what they are, but they're heavy. So we did do a study with it, but this Espagrandes itself weighs 300 kilograms of metal. It doesn't do anything for you. It's a spacecraft bus. But we looked at it. What could you do with that? And you can actually almost make that work. But I kind of prefer just the standard spacecraft, with panels and stuff. Instrumentation. We loaded this up with kind of your standard flight. Now, some of these are small versions or lightweight versions, and, kind of Neil's maybe CMI version for the magnetograph, or, and chronographs, maybe a C-core-like version of the magnetograph. So these are small things, but we wanted kind of a standard suite of instruments that one would have. This is not just 1 or 2 instruments on it. This payload would fulfill, other than if you wanted 6 months over 1 pole. That doesn't do that science. But this mission would do a lot of the science that we talked about here. Of course, if you had infinite money and launched 3 or 4 of these, then you can do that. But that's more that the design that I think that Don was showing about. That would be the basis if you're launching a constellation, would be the small sat version of this. This was putting everything on board. So I think I said everything on this slide already. Again, this is feasible. With current technology, nothing new, nothing strange. The new part is getting someplace we haven't been to, and that's why we're here this week. Is we all know it's exciting. So I think it's achievable. I'll go ahead and mention a little bit of budget, because we actually have done a full cost on this. This is kind of the STP, the Solar Terrestrial Probes class-ish mission. And you can look up whatever the IMAP cost was. I don't know, it's probably $750 or something like that. By the time it's said and done, and you can inflate that to whatever year you think this would launch, and there you go. But it's of that order. It's not, you don't need $2 billion, you don't need $3 billion. This was the intent here, was to start to form real missions so that we can begin to get, I want to get you all excited. I want to get the rest of the entire community excited. What can we actually do now? What I don't want to have is, I'm going to go back into maybe to tomorrow's discussion a little bit about the decadal surveys. What I think was going to be really important is not to fall into the trap of Interstellar Probe did last decadal survey. So what they said last time was, boy, that's a fantastic mission. I'm not going to talk about it anymore because I can't do it. I want to make sure we can do a mission, a solar polar mission, the next day. So we need to begin to temper a little bit. I'm the same person who said, don't worry about technology. So it's that you have to find that boundary, that mix, and this went maybe one step a little bit closer. Now, optical comm would be fantastic. This does, for the telemetry rates that I want to get out of this mission, I probably do need optical comm. It would be, or a really smart computer. But these are things that are achievable. So I think this is a strong candidate for a big future class mission, of strategic level mission for achieving a lot of the science that we discussed this week. And that's it. Thank you.
Thank you, Jeff. we have questions? I had one actually real quick. So you had several Earth gravity assists before you got to Jupiter in several cases, which let you get this large of a payload out to Jupiter.
Yeah.
But you also had some orbits that had direct injection to Jupiter, right? Or do they all have to use Earth each?
No, I think there were some that had direct. They weren't necessarily fast, and I don't know that they caught the inclination necessarily that I wanted. I think that it helped to hit. I think it didn't. I think there was no benefit of going to, for this class mission, there was no benefit of going direct to Jupiter. It actually took me about the same amount of time to hit the Earth and get you there a little faster and get a little bit more oomph.
And that's the solution that many planetary missions use. I mean, they do an Earth gravity assist and then they whip themselves out to where they're going.
Yep.
Okay, any questions?
What the technological development has been the main motivation for this since maybe 10 years ago?
The biggest development for this has actually been the solar electric propulsion. 10 years ago, if we were in this room, we'd be talking about, well, does that really work? And Hayabusa had just flown or just launched. I forget when Hayabusa launched, but it had this little small Hall thrusters on Hayabusa. Now, the commercial world uses Hall thrusters, which is another version of an ion engine. They're related to both solar electric propulsion. They use that all the time. So they're beginning. Dawn is launched in 2010, or I don't know. Somebody can remind me when Dawn launched. As it was an SEP. So it really is the practical use, the demonstration that this is done, and this is where maybe 10 or 15 years ago, what Paulette was saying was there was kind of an unknown which technology would be more mature at this point in time, sales or SEP, and I think. For at least today, SEP has won that race. They are more mature today, and they allow you to do this circularizing. Otherwise, as Paulette showed, you could have done this mission, was proposed in 1980, whatever, for ISTP. I'm really not having that much different than ISTP. I'm just circularizing it.
Any other questions? Yep.
I guess today's my day to be the inverse square law guy, but at what radius from the sun would the 1 over r squared power production rule break down for typical solar panels? I mean, obviously at some place they get too hot, they don't work anymore, but the closer you go to the sun, the more power you get and maybe the more thrust you get. How close do you get to the sun before that inverse square law breaks down for
it doesn't break down. It doesn't break down, but I said what I studied, and we studied a very specific real thruster. I'm not a fake thruster, not a hypothetical one. We studied the next thrusters. These have been built on the ground, and that uses about 8 kilowatts of power. So this is a very specific real one. That's the maximum. So I can't give it more. It doesn't do any more. I can put more of them on, more money, more mass. I can put more of them on, and I can get my arrays. But at the half an AU, again, I don't really want to go in any closer than a half an AU for the thermal reasons. Because I'm already out that factor of 120 in thermal input to my system. So I don't want to go any closer, anyhow.
Any other questions? Thank you very much, Jeff. Okay, so our next speaker, and I think the last speaker of the session before the panel discussion, Tom Berger from CU. We'll talk about his Solar Polar Observatory constellation.
Walked off with your...
Yeah, don't do that.
Fuck. I like the name.
Yeah, so Jeff, we actually looked at that question of where does the 1 over r squared start to get you on the SCPs, and it's about 2 AU. So I'll show that in a minute. 1 second. Right, yeah. But you can use them farther out, but you have to be within about 2 AU before they work. Yeah. Well, I don't know. I'll show you a slide. Anyway, this is a talk pretty much repeating what's already been said, which is using gravitational assist from Jupiter and solar electric propulsion. I think we have a feasibility to do a polar orbiting mission here and circularize. I'm going to talk about this particular mission, which is circularizing for a different reason, and it's really based on a different requirement set than pure science, and it's because we've got this new center at CU now called Space Weather Trek, and essentially what we're aiming at with Space Weather Trek is to both gather a lot of the space weather capabilities at CU, which already exist under one easy-to-access group or center, but also to interface better with the operations world, and that's something that's been kind of lacking in a lot of the research centers in the past. And so I'm going to show a quick slide here to outline what we're doing with Trek in terms of what we call the enterprises, because, you know, get it, Star Trek, Enterprise, Office. So we have the research enterprise, which is concentrating on modeling essentially the ITM system for the application in the operational world of satellite drag and space traffic management. So that's our main research goal. That's really being handled by the Aerospace Department and some people in APS. We're also developing a deep learning lab for solar flare forecasting, for instance. We're going to be working with some people at LASP on that problem. That's just getting started. The other enterprise we have, or one of the other enterprises we have here, is called the MADTech, which stands for Missions, Applications, and Data Technologies. That's really run out of LASP, and it's people there who are working on both a data portal to collect space weather data in one easy-to-access interface, web-based interface. We're also going to be developing a space weather test bed, which will be an operational-like test bed for research models to come in, be shaken down in a research-like environment before getting passed off to CCMC for final verification validation. So we hope to have a step in there that's currently missing, where the forecasters can easily work with researchers, get the thing working in an operational sense before you send it off to CCMC for V&V, and then send it over to NOAA. Currently, the cycle is it goes from researchers to CCMC to V&V to NOAA, who says, oh great, now we have to operationalize this model, and that actually takes anywhere from 2 to 5 years, as it turns out. So we hope to help with that, with the test bed and the data portal. And then you can see some of the mission concepts we're developing here. And each one of these mission concepts is based on this idea that it's a hybrid operational research type of mission. So one of the ones we've been asked to formulate by the DoD is a follow-on to the Van Allen probes, because the DoD, somewhat like SWPC, sort of came late to the game to the Van Allen probes, got all revved up to put Van Allen probes data into their product line, and then suddenly found out that it's actually dying next year from fuel exhaustion. So they came to LASP and they said, what would it take to replace the Van Allen probes in an operational sense with small sat solutions? We're working on that. But that would also be a real-time or near real-time data flow through TDRS. So it'd be much, much faster data than Van Allen probes, and therefore could potentially be a great boon to research in the magnetosphere as well. And then you see below that the Spock mission, which is similar. We're now aiming at a full sun, as I'll talk about, magnetograph, coronagraph capability for operations primarily, but also, as we're hearing this week in this meeting, this would be a tremendous boon to research on the solar magnetic field as well. And then finally, an EUV occultation CubeSat constellation. We're working with Spire to measure EUV occultation through the thermosphere and get thermosphere neutral density, again, for satellite drag applications there. And then the final enterprise you see there is education. That's being led by Steve Cranmer of APS, and he's got both online capabilities with the COMPASS program that's existing with NSO, and he's also now the dean of the new Boulder Space Weather School, and he's contributing to the NASA Heliophysics School as well. So that's kind of Space Weather Trek in a nutshell, and now I'll focus on the Spock mission in particular and why we want to do this. And this really goes to the heart of the problem. This has been talked about here, but I don't know that this type of slide has been shown. Magnetograms really only work out to about 60 degrees from the sub-Earth line on the sun. So you're looking at a disk on the sun, which limits you to your data collection. So for instance, this active region, that active region there is outside that 60-degree range. Signal to noise for that, except for horizontal fields, is going to be too low to include in any sort of synoptic map. And so really, you're ending up with this point that from one vantage point in the ecliptic, you get about a third of the sun at any one time. And of course, none of the poles. So that's kind of just repeating what we've been talking about here. L5 to the rescue. This is something that some people have been talking about. They get excited because they think you can cover more than half the sun, maybe 240 degrees. Actually, if you take into account the 60-degree limit, you're only getting about half the sun with L5. L5 also has this tricky thing that it's, because of the ecliptic tilt, it's looking at a different latitude range than your Earth-based magnetogram. So you've got tricky issues there in merging data. In fact, to get full coverage of the sun using Lagrangian point orbits, you need L4, L5, and L3 to get the backside. So I don't think that Lagrangian points are really the issue, the solution that we should be looking for if we want to go for the full coverage of the sphere. So what have we done? We've done the workaround, of course, which is synoptic maps. And this is showing the classic construction of synoptic maps using the central meridian strip and just letting the sun pass below that central meridian strip. This is the HMI method. Gong has a more sophisticated method using a full disk of the sun really and integrating with a weighting function across the disk. But this is the simplest way to understand a synoptic map. It's not an image, it's a time-based map, time going in this case from right to left to create a synoptic map. So one of the errors we all do, of course, is say, well, that's the sun because you have longitude from 0 to 360 and sine latitude from -1 to 1, so why not wrap it around the sphere? And there you go. That's what we all think of when we see these synoptic maps. But of course, this does not exist. There is no such thing as the sun looking like this at any one time. And so when you take this and put it into a solar wind model, you understandably are going to get the errors that we see here, for instance. So this is a demonstration of the WSA model run with Gong and the zero-point corrected version of Gong shown on the left there. And you can see with the solar wind solution in the middle there that we missed that high-speed stream. And this is actually, I think, October 2016, sometime like that. We missed that high-speed stream. That actually turned out to briefly be a G3 storm that was forecast to be at most a G1 because wind speed was supposed to be way down. So that's a consequential event. A G3 is not, it's not nothing. So that's a good example of when you're just using Gong with its relatively weak polar fields, you get something like that. Whereas on the right, I'm showing if you use the ADAPT model, and I'm sorry I missed your talk this morning, Carl. You may have talked about this and maybe even mentioned this event, but essentially the ADAPT model, as I think you probably heard from Carl, is able to flux transport down to the poles, increase the polar fields as you're seeing there in the upper left to such a degree that you actually pick up the right connections to the coronal hole system, you pick up the high-speed stream correctly. So had ADAPT been working at this time, SWPSI might actually have forecast at least a G2 for that event. So this is just by way of saying that the polar fields really do matter for space weather forecasting and operational forecasting. So we've got to get those polar fields right. Now, how do you do that? That's what we've been discussing in this whole meeting this week. And this is our particular solution. We're working with Ball Aerospace for the Spock mission, which is a constellation, ideally here, and this is really just ideal pie in the sky. What would we want to do to capture both the poles and 4 pi steradians of the magnetic field through a multi-spacecraft mission? So I'm showing here sort of the rough outline of spacecraft in 2 planes, each orbiting over the pole, 90 degrees ideally. We've got identical satellites. We've got simple, relatively operationally focused magnetograph and coronagraph instrumentation, in situ instrumentation as well, of course, because it's cheap and easy. But you're also getting the research out of it because you're going over the poles, so it has the discovery mission aspect to it. This is the instrumentation examples we've looked at. Neil talked earlier about the CMI. This is a really nice instrument. It's low mass. It's hard to read here, but just to refresh your memory, it's 33 kilograms with electronics, I believe, Neil? Yeah, so that's 33 kilograms with electronics, ready to go. 2K by 2K detector, 1 arc-second resolution at 1 AU. I'm sorry, 1 arc-second pixel, so 2 arc-second resolution at 1 AU. Relatively compact volume. That's a really nice candidate magnetograph, I think, to fly. On the other side, I'm showing the NRL compact coronagraph that's been developed for NOAA for many years now. This may or may not be what you want to fly for your CME imaging, but this is one example of what you can do in a compact instrument. This is a field of view of 3 to 17 our sun, about 0.7 meters in length, 13 kilograms, 60 watts, again, comparable in compactness to the CMI. But as we heard this morning, and/or maybe you want to do an HI. So we have to go and look at that and do the trade space on the HI instrument, see what kind of weights we have there. Maybe that's an and instead of an or, I don't know. But that's the kind of trade space we haven't gone into yet. For the in situ instruments, showing here the Van Allen probe's magnetogram, or magnetometer rather, which weighs all of one kilogram, about. And so that's obviously very light and compact. It does require a boom to get you out away from the spacecraft, but that's also pretty light. And then on the other side, I'm showing the Parker Solar Probe Faraday Cup and both the electron and ion electrostatic analyzers. I couldn't find a weight for the electrostatic analyzers. I'm guessing about 5 kilograms. But the Faraday Cup's 4.5 kilograms. So the in situ total here is about 10 kilograms as well, including electronics. So if we total up the instrument mass here, we've got something like 60 kilograms, using kind of the rule of 3 for spacecraft design, which is your dry mass spacecraft is about 3 times the instrument weight. We're up to about 200 kilograms in spacecraft weight dry mass. So what we've gone and done now is sort of defined our parameter space, which we're going to narrow down in the future in trade studies. And so this is what Jeff Van Cleve here from Ball has been doing, looking at a range of things on the semi-major axis, anywhere from the Mercury orbit, which, as we all have heard in earlier talks, is thermally very challenging, out to about 1 AU, and also and the relevant periods there, and inclinations anywhere from 60 to 90 degrees, again, depending on your spacecraft mass to Jupiter, and in the particular approach to Jupiter, you may not be able to get to 90 degrees. So anywhere from 60 to 90. Eccentricity, we'd like to get below 20%, because we don't want in the final circular orbit to have our plate scale changing a lot on the detector. So ideally, you'd like to have a stable plate scale. And Jeff is showing here sort of the 4 different longitudes, the delta longitudes, which would put the 4 spacecraft at different longitudes across the sun. Now, how we get there, that's still being developed. So Natasha Bosanek here at CU, who's in the Colorado Center for Astrodynamics Research, has done some preliminary orbit calculations. This is showing, again, as the previous talks have mentioned, we're basing this on the Ulysses orbit. And what you're seeing on the left there is a plot of when you leave Earth, when you arrive at Jupiter, and the delta V necessary. And there are these nice dips where this one is showing if you leave in, October of 2025, you arrive in 2027 at Jupiter. And that only takes about, it looks like 10 kilometers per second, something like that. So that's doable. What she then did was take a conceptual circularization, in this case to 0.93 AU. So I know the abstract said 0.5. People have talked about the orbits of 0.48 being advantageous for your phasing with the Earth orbit. But Natasha just took this one to 0.93 to see what would happen. I noticed you used a very large spacecraft mass. So this is 1,500 kilograms. So we're not saying we have a realistic launcher out to Jupiter yet for this, but she didn't worry about launchers. But that is a realistic mass for that ion engine, 0.2 newtons, 3,100 seconds, which is actually less than what Jeff was showing for the next engine. So it'd be nice to redo this with the next engine. That'll be a nice augmentation of this. With 600 kilograms of mass, you have, again, 3 orbits to circularize down to about 0.93 AU. Final eccentricity is 0.03, so it's a very circular orbit. And the idea also here is what we'd like to look into, I'm showing on the lower graph there, is if you took 2 of these out to Jupiter and were able to put one to the south and one to the north, and then flip them over the ecliptic in different directions, you end up with that counter-rotating plane of spacecraft that I showed in the first slide. So again, not sure this is totally feasible yet, but this is what we're aiming for ideally. And the key strength here is that you get polar science over each of these orbits. Now, this is to Jeff's point earlier that you can't thrust all the time with the ion engine, but what you can do is what Natasha has done here is shown that within 2 AU, you turn on the ion engine, and you're thrusting over these red arcs to circularize. And so that's getting the circular orbit pretty quickly. This is a plot of something like what Don showed earlier, solar latitude versus distance. And you can see we're coming in from the upper left there, from Jupiter, after the gravitational assist. In this case, in 2.46 years, we're over the pole. So this is, as mentioned, astrodynamics voodoo, but I think it's real. It's probably real. given that these programs are pretty well understood. And you see you have a polar pass then every sort of year after that. So one spacecraft here is going over the North Pole and the South Pole repeatedly, and about 7 years later, you've circularized. And so that is the extent that we've got now. This is, again, just highlighting those polar passes. So this is when you're doing polar science. 7 years later, you're in a circular orbit, which is your final operational orbit. You've got a stable orbit for a stable plate scale. You've got polar views. You've got, hopefully, eventually, a constellation giving you the 4 pi steradians of the magnetic field. And yeah, that's the idea. So key trajectory design questions we're working on now. We've only been working on this about a month and a half now, or something like that. So this is really early, but I think it, again, as Jeff and Don have both mentioned, this seems feasible given current technologies with solar electric propulsion. So these are the things that we're looking at, including the range of values for spacecraft mass, of course, the thruster properties, and again, this idea that the 1 over r squared does affect you with your solar panels. So I'll just leave it there and take questions on this concept. Thank you.
Very nice, Tom. I have a question before anyone else starts. Running the ion engines for such a long period, would you take science data at the same time? Because
No, that's a really good question. You're thrusting in the anti-velocity direction, so ideally you could be looking sunward.
Right. Possibly.
I don't know. Something we've got to look at that.
That's one of the things, that's why when I said you can't do it all, because it takes a lot of power, and the ISP I was showing was for close in, we're getting full power. Again,
Yeah,
I was
so
not
it's gonna-
using 30 kilowatt worth of arrays. I mean, it's power. So if you have
Yeah.
more power you have,
I
so
don't
you can do more.
I think she changed the thrust and the ISP per burn there. I think that's assuming a constant ISP.
Well, it's an interesting question, because I think actually NOAA is considering this, and there was some requests for tech studies a few years ago to see the impact of ion engines on all the different suite of NOAA instruments for space weather, the in situ package that you showed. And I don't think that mission ever flew, but there was, proposals to do that. I know I wasn't actually involved in one with Bo. Vic.
Send a very small spacecraft kind of in a better orbit. But anyway, we looked at the ion engine business. There were 2 issues that were kind of wasn't really resolved one way or another. But one of the questions was contamination from just what you're exhausting. And secondly was vibration. And as because these things, at least at that time, were kind of bumpy and you'd shake the rocket or the spacecraft a little bit. I was wondering if there'd been development since then.
Yeah, I don't know. I'm not an ion engine specialist, but I'm sure there has been development since then. But whether or not there's still vibration, whether there's contamination we have to worry about relative to the instrument pointing, these are all things we have to look at. But ideally, this is, again, just pie in the sky right now, seeing what this sort of orbit trajectory would look like. If you could fire your engines as soon as you are within 2 AU, that's what it would look like. And you would get down pretty quickly, so.
Oh, and even just a pair of spacecraft going to Jupiter and one going north, one going south, that gives you already a lot of leverage on your observations.
Yeah.
Any other questions?
As you point out, that's all about mass and rocket, but, apparently these things the mass is going down, the rockets are going up, so.
That's right.
We're in the right direction.
Anyway, good. Well, thank you very much, Tom.
All right.
Very nice.
Okay. Let's have the invited speakers come for a panel discussion now. I think that's good. Okay, so we have, where's the other microphone? Here's one here, there's one over there, and let's bring this here. Yeah, bring up chairs. Go ahead, just join in with it. Go ahead. Okay. So I'm going to kick things off with a question. We've heard a lot about a lot of different kinds of mission designs. We've heard about some that are ready to go out the door right now, some that may be down the line. We know that the way funding works, there can be different kinds of solicitations, different kinds of opportunities. We heard Paulette talk about a fractionated approach, and I'm wondering if the concept of a fractionated approach extends beyond within a mission and can also go to between missions. And so the incentive for getting something out as fast as possible as a pathfinder, and then as the opportunities arise for the large missions, start getting those out. This extends across national boundaries. You might imagine that JAXA or ESA or China or anywhere might be also sending out missions. We see the benefit. We see that there is no one mission that really achieves everything, because even if you put all the instruments on it, you wouldn't necessarily get the 4π. So there's a huge benefit to having lots and lots of different observations to really fill these gaps. So my question for you is, if this is actually the way this may play out, and it may be, what would it behoove us to think about now in terms of standardization, in terms of agreed upon requirements? Are there instruments? I mean, we talked about observing BZ with Faraday rotation. If every single spacecraft had something that would then be able to communicate with the others, would that be worthwhile? I mean, let's break open the box here and think, if we could design this as the next 2 decades strategy, being able to be incredibly flexible and reactive to opportunities, what should we be thinking about and talking about now? Long question. Let's hear what you say.
No, I think it's a really good question. Take the Lagrange L5 mission, for example. It's an ESA mission, part of the Space Situational Awareness Program. So it's not a science program. But the science director at ESA is interested now in it. And he's actually interested in seeing that science come out of it. So when the SSA program is putting requirements on the Lagrange mission, which has, let's say from a remote sensing point of view, it has a magnetograph, EV imager, chronograph, a heliospheric imager, et cetera, and so on. There's standard measurements which aren't so different from the types of measurements we want to take from the polar perspective. And if we're roughly at 1 AU, whether it's at L5 or over the poles, those instruments have applicability. The thing that for the magnetograph for L5, if it's purely space weather, they don't seem to care about the Dopplergraph part. They just want the magnetograms. So we need to make sure that, well, certainly Max Planck, who's the candidate to build that magnetograph, will ensure that there's that Dopplergraph capability. So that's not a question, but from the point of view of ESA's requirements, standardizing requirements, or at least having agencies talk about, what types of observations ought to be standardized for this, because it is true that if we had a polar mission at the same time as Lagrange L5, then if something happens to SDO, we still have L5, or whatever other assets we have, and I think it's a really good way to collaborate across agencies.
I'll add that, I think it's exactly right. I mean, I think that none of our missions are going to do everything. And indeed, the US is not going to do everything. And so we do want to be able to seed, I think, things. And the one instrument to me, in hearing these discussions, that lends itself more to standardization is the magnetograph. An EV imager, okay, they're all a little bit different, but nobody really complains that you can't co-align or you can't use the same emission measure from one to the other. On the other hand, we can't get 2 ground-based magnetographs to agree, yet alone HMI and MDI don't agree with GONG. And so that seems to be the one that stands out in my mind. And in situ stuff, they'll roughly kind of agree. I mean, composition would be great for everything, but everyone will kind of agree, okay, yes, here's the 06 to 07 ratio, great. But the magnetograph, other than sea change things that Neil is going to come up with, which is just going to throw it all out, I don't know. But if we all, if we all look at a different line, which is historically what we all do, everyone builds the magnetograph and says, this is my favorite line. I'm going to look at the green line. I'm going to look at this line. I'm going to look at, then we're going to have a little bit of an issue for trying to combine that all into the 4 pi steradian world. And I don't know how you enforce that, but it's back to Don's requirements, maybe, is that intercalibration part. Maybe it is just an intercalibration on the ground, that there's actual money for ground intercalibration.
So I think we do have some experience on this, looking at the heliospheric observatory in general, and we do have a lot of experience, like he said, with the different imaging instruments. Somehow we do seem to manage to put this together. But the magnetograph is an issue. I want to comment on what Don said, that L5 wouldn't want the Doppler measurements. Is that what you said?
ESA, ESA SSA, the program.
Oh,
which
they
is
don't,
Space
okay.
Observatory.
Because I think in general, we do
No,
want
the
to have,
scientists want it.
right, we want to have that 2 viewpoint helioseismology.
Agency doesn't want to pay for it.
Gotcha.
This is going to apply to the capability of small sats, which is something I talked about, I think Jeff chimed in on. There are going to be missions of opportunity now. That's something Dr. Zabukin has talked about, is anything that goes beyond LEO, they've got to make sure there's always a mission of opportunity that's attached to it. So if there are worthwhile measurements and you have a lightweight instrument, take advantage of the breakthrough and the revolution in these small spacecraft to see if you can fit something in the box. And design to cost, design to capability, if it's going to be good science, because I think it's got a really high lever arm in terms of the cost-benefit ratio. And I think Marco, what we're doing, a lot of the small sets that are going to be flying, I think this is kind of a golden age for the small, lightweight, quick, responsive mission of opportunity.
I just want to echo what Jeff was saying, that if you're going to fly magnetographs in space, try to standardize on that. It's going to be difficult to intercalibrate them if there are different lines, different instruments, different filters, different cameras. It would be really good if we could standardize on a space magnetograph that would be on lots of different viewpoints. I also want to go back to my statement about ground being impossible to intercalibrate with. It's possible, but it's spatial resolution dependent because the ground has seeing. So if you don't, and this is a question I have for the modelers, what resolution do you need in your global spherical magnetogram map to achieve your model resolutions that you want? If you're okay with 10 arcsecond resolution or greater, then we can do a fairly good intercalibration between a space-based and a ground-based magnetogram that's relatively stable. But seeing is very unstable for any ground-based system, even a network. So that's that's essentially the trade space you have to look at there, is what resolution do we need to create the spherical, the 4 pi magnetogram for the inputs to the models. If they can tolerate very low resolution, then it's probably going to be easier. If they need the high resolution, then I maintain that it's going to be extremely difficult, if not impossible.
Yeah, and as far as the requirements go, I think since each of them are going to be agency specific, they're all going to have their own requirements, it's going to be difficult to have a standard, in the case of magnetograph, to have a standard. I think it's almost going to have to be a gentleman's agreement that, we'll promise to do something even though it's not required, which if we all work together somehow, but I think that's going to be a challenge.
The other thing I wanted to bring up was this optical communications. We talked to some people at Goddard about optical comms to a mission going out to the sun, and they said, oh, the sun, that's real bright. And so if you're talking about laser comms pointing to the sun or near the sun, you've got an issue there. So it's possible, you just have to make sure you have a wide enough margin. The other thing that I didn't mention is we haven't discussed the fact that optical comms require another telescope. So that's a whole other optical system. And it requires a ground system as well. TDRS is probably going optical, so that's going to help, but you're talking about half-meter class telescopes as your ground system.
Yeah, that's true. The optical, you need an infrastructure on the ground, and it is true for solar observations. But I mean, yeah, well, you could have Earth orbiting, and then you downlink it easier. But all the ground stations would generally be at high latitude for the solar observations, which we don't have. So like in Norway and Alaska, or in the southern hemisphere. But that infrastructure isn't there and needs to be developed.
There's no real difference in principle between radio interference from the sun and optical interference from the sun, right? I mean, if you're off to the side, you should still be able to see your beacon.
Yeah, I don't know. I mean, that's just, I'm just relaying what I was told when we brought this up, that, hey, we're going to sort of 1 AU near the sun and we'd like to have optical comms. And they said, that's interesting. We've never thought about that. They're going in the other direction, typically to planets or the moon. Yeah, so it is an issue that would have to be worked. And again, it is a telescope on your satellite, so another telescope.
Is there a possibility to do something with a relay, with a shared resource that all of these different fractionated approaches might be able to use to help with telemetry?
Yeah, I was going to add as far as the going to the optical. I mean, one point is that there's a lot more optical power, but the other advantage of it is a smaller angular coverage that you have to worry about. And the other point is that we can use the same sort of, this spider instrument, part of its design was to enable laser comm. So we could have large flat panel display systems rather than telescopes.
Oh, that's
Let's open it up to questions from the audience. That's okay. It was open, but now I'm encouraging you.
So just a point of clarification before I get to my question. If you want to hear me complain about UV imagers and calibrations between them, please come to my office later and we'll have a large discussion about them. But my question is more about the balance between using existing technology versus innovating new technology. And I know that for Parker Solar Probe, that new technology for the heat shield for the solar arrays was a real big driver for why the mission got funded and got pushed to the front. So I just want to hear your thoughts on what is the right balance to strike between using existing technology that is ready to fly right now versus pushing a concept that is on that will push the technology into a new frontier.
Well, I think that's a hard issue. I mean, that's part of the reason they have this tech demo going on now, is to try and inspire people to innovate more and actually get it beyond the TRL 4 or 5 level. So I think that's always a tension that particularly for something that might be operational, is you want to have something that you know what the answer is going to be, rather than something completely off the wall. But I think there's opportunities here. NASA's eager to push this, so I'm hopeful.
So usually, when you're proposing missions, if your technology isn't ready, that'll really count against you. In general, if it's any mission, technical review board is going to be very down on any new technologies, because you might get into a situation with like JWST has, where it's just going on and on and on, because they didn't really have the technology. So generally, unless it's a tech demo mission, and of course that's what we really need more of.
Well, so it's true, but I think for the first polar mission, the orbital vantage point will give us discoveries by themselves, and the mission itself, maybe the mission design will be the biggest risk, and you want your instruments to be straightforward and high TRL. But if you think about in Bob Ergin's language from yesterday, the second generation of missions, when we start to hone in on very more detailed quantitative questions and more complex issues, we definitely need to be spending money and time on doing these technology developments so that new instruments will be ready down the road when we need to be using them. And we should be doing that now. I mean, I think that's one of the biggest challenges is, and this is it's always a frustration. Do you fly the same thing with high TRL, or do you do something new?
I would just add, I briefly mentioned this earlier, this dichotomy where Don and I presented kind of things that you can build today. All right, so that's clear. You can do those. hovering over the poles, less said I can do in 25 or 30 years from now. So if we're thinking of things in the 10 to 15 year time frame, meaning it's going to be in the next decadal survey, here's what we want to, as a community, think of what science we want to do. We really want to nail that science and then say, okay, here's the technology investments that you need to do today to enable that science. And that becomes the real mission then. So that becomes when the AO comes out in 2026 for that AO, that for a mission that launches in 2031, then the technology is ready. So we should be really thinking hard for our dream mission, but I mean, hover the poles is maybe one step too far. That's 2 decadal surveys away, probably. But 1 decadal survey away, that's near-term technologies where we can say that if you target now the technology through and this is fantastic. I mean, kudos to headquarters for putting this the tech demo AO out that Les mentioned. This is the first time we've done it in heliophysics. We got to reinforce to headquarters that this is a great thing and that we want more of it and continued of it. And one way to do that is to identify the greatest science in the world, Nobel Prize winning, what are we going to discover up there? And then say, here, if you just target that technology, it's going to win. And I think that's how you do it.
I hate to be the Rodney Dangerfield of this, but the last decadal survey was very clear. Invest in solar sail technology. Do it now. Do it well-funded. Yeah, it does. There are lots of places in there that call for that. That fell on deaf ears in STMD because the people at headquarters at the time, and they're no longer there, when we were doing the Space Technology Investment Plan, and I was part of the Roadmap 2 in space propulsion technology and such, and we had to go back and get to the science directorates to tell us what the biggest pull was, and it was supposed to be in the decadal survey, so I was real excited. I had heavy pull. The people at headquarters at the time said, oh, that's not a priority science for us. We're not, even though the decadal survey says you need to do this, that's not what we consider to be the highest priority missions. We're not going to do that. And so we got no official pull for sales in the technology plan that went to STMD. And so you can have all the great pull in there you want, but I find personally it's all opportunity and people dependent, and we've really got to work that. So again, I'm not trying to be the contrarian, but.
No, but that's the difference is when I was talking about technology investment, I was talking about SMD technology investments like they're doing now. STMD is owned, run by human exploration. If you are not tied into human exploration, don't bother going to them. I've been at headquarters for 8 years. That was how it was. That's why we are not part of that. But if SMD investments in technology, they invested in MMS, FPI, getting 100 times faster. So Bob talking about it was the particles were 100 times faster than the previous generation for FPI. That was an investment. Probe, getting the targeted JW, even though it's costing $10 billion and 20 years to build, the targeted that kind of stuff SMD does by itself. If we have to rely on STMD, we've lost. And I'm just telling you, in the future, it's even going to be even worse. It's going to be Moon and Mars.
Michael.
Yeah, I wanted to kind of get your view on the kind of separation that I think is necessary in approaching the next steps. On the one hand, we have the issue of monitoring the sun more or less in the ecliptic, but all around. And the technologies to do that to an accuracy that will then allow for initiation for numerical space weather forecasting, all of the physics there isn't out of reach. So it's more like that you need a big effort to deploy enough observational tools that cover the sun from all angles. And that is a necessity that all sort of high-tech economies on the planet share. And the Japanese, the Chinese, the Russians, the Europeans, and the US basically share that concern. So it could be feasible that you could put together and join forces on this. Now, to me, the solar polar missions, of what flavor they are in detail, I don't care for a minute. But in working in this field for all my career in one way or the other, we've come to the conclusion we really don't understand how this dynamo thing works. And if not for studying a gazillion other stars, and in that way back mapping what the sun might be doing, the only real gap that we have is the detailed studies of the solar poles in terms of motions, in terms of magnetic configurations, and what have you. And for that, I think that's really where the justification for a billion-class science effort should be. And again, it could be that you need several probes, but what you need that part needs to be sophisticated, and it needs to be high resolution. So, anyway, for what it's worth, that's how I see it, and maybe you can comment.
Well, I agree that it's, the polls are the compelling motivation for this. I don't know, from a point of view of relating it with the other agencies, it was kind of similar to, I think, Sarah's original question about standardization, but maybe Tom.
Yeah, I agree that, and I think it was Lisa who said, a spacefaring society that doesn't monitor their central star is really stupid. That's essentially not, paying attention to the weather when you're sailing across the Pacific in a sailing vessel. So we need to monitor the central star. Now, the question is, can we monitor the central star, give the operations community what they need to do their forecasting of space weather, and at the same time, get some science out of it? And I believe we can. I believe that's why these missions that are hybrid operational research have some promise, because you do get interest from the DoD. There was a meeting I was at recently where an agency person that I won't identify came kind of bursting into the room and saying, "Did you realize that all of our operational space weather missions are run by NASA?" And, and that was some sort of news to this person, and it was shocking that these were not considered operational missions, because they're not. They're one-offs. They can break. They can disappear tomorrow. This was, in specific, SOHO. He was shocked that SOHO was a one-off that was actually on its way out. So I think there's room to discuss with these other agencies that, yes, we can monitor with these instruments and give you the data you need to do the forecasting, but we should also be keeping in mind that these instruments don't have to be 256 by 256. They can be 2K by 2K detectors. They can give us some good science while they're doing it.
If I may, I'd like to refocus back on technology for a moment, which is we've seen a lot of discussion of the various technologies, thrusters, communications, this kind of thing that need to be developed. I don't see anything that's a showstopper if we had a large enough rocket. Is there any reason we couldn't just do a direct injection with a Cassini-like Ka-band antenna tomorrow on a BFR?
My orbital dynamicist says you can only get about 30 degrees out of the ecliptic, even with the giant ones, but maybe you guys.
The orbit guys at JPL that I've talked to only know Jupiter and solar sails. I don't know how long it would take a next ion engine.
No, I think he's talking about direct rocket.
Big rocket.
Oh, rig rocket.
Or say even with Jupiter, do you actually need optical comms? Or if you had enough mass, could you just fly a regular old radio?
Well, the telemetry, I mean, it depends on what pipe you need. Ka band's actually pretty good. It's enormous. It's an order of magnitude better than X band in almost all orbits. In terms of the direct injection to high latitudes, you have to negate the entire 27 kilometers per second velocity of the Earth as it goes around the sun first, and then all you do is fall into the sun. Then you got to, get the C3 to get out of the ecliptic. So, it becomes astronomical, and that's not, it's a great idea, but going to Jupiter is a lot easier to do.
Yeah, I mean, exactly. No, even the BFR is not going to get you a polar orbit directly. What those bigger rockets do is they can get you more mass or multiple spacecraft. I mean, if Tom wants to launch his 4, then you use Jupiter Gravity Assist exactly as he's showing. You can launch all 4 at once. That's what that can do. But Jupiter has a lot of mass. It's a lot of C3 to, a lot of delta V to get rid of, to get up there and.
I'm hearing if you didn't want to go to Jupiter, you would need more propulsion technology. I still haven't heard anyone say we absolutely need optical comm.
No, optical comm is just, it's that whole trade-off that we've discussed in other things, is how many magnetograms do you need? Do you need it 1 arc second, 1 minute for all the time? Well, then that's probably going to need optical comm. So exactly what resolution do you need over what time scales do you need? And that's a trade-off versus, again, this is one of the things we should think of, is future smarts, right? We're right now onboard processing are, 15 years behind ground-based processing, maybe. I certainly know my iPhone is way more capable than all the spacecraft that have flown, that NASA's ever launched put together. And so what can we do in 15 years? I don't know.
So Craig, with just Ka band, you can get 20 to 100 kilobits per second, something like that, depending upon where you are and the size of your antennas, et cetera, and so on. That's in that range. Maybe twice that, or order of magnitude more than that. But if you had a whole suite of instruments like Solar Orbiter with ultraviolet spectrographs and other spectrographs in addition to your magnetograph, and if you do vector magnetographs, and you have many remote sensing instruments, a whole suite of ultraviolet imagers, you do the second generation type of emission. That's when you're starting to get your telemetry up to where I think optical comm can benefit. If you're doing something that's targeted and focused, K-band works quite well.
Consideration there is ground stations. If you're reliant on the Deep Space Network, as SOHO is, then you end up with 9 to 10 hour gaps frequently between data downlinks, which begins to be non-operational for certain agencies. And so you really have to think about ground stations when you think about comms and cadence.
Okay, if we don't have any other questions, I wanted to, this is actually a good transition to have a brief discussion or brief explanation of what's going to happen tomorrow. Because tomorrow, you may have seen that our ever-evolving schedule on the online is a little different than what you got handed at the first part. So originally we had talked about designing your dream mission, but let's not do that. I don't think we have exactly, I don't think that at this point with this group is necessarily the right thing. We've heard of some wonderful dreamy missions today, for example. Rather, the idea is we're going to break into the science subtopics. And the poster on the wall has an example of how this break may work, and this is where we're starting from. Solar interior, global connections, and heliosphere. The poster also is a paper that appeared in Frontiers this week, so you can see it online if you don't want to go look at the poster. And so this groups some of the science questions we talked about this week. I think most of them can be thought of in those terms. The interior clearly connects all those polar flows and fields and those issues we talked about, and the global connections is a bit more broad, but it connects to the origins of CMEs and the solar wind, and also how everything is connected and evolves. And the heliosphere is then the evolution and the changes in the heliosphere. Space weather, which in that poster and in the paper is its own category, can really kind of be tagged onto any or all of these. These are just notional. But the idea is to break us, but it kind of breaks us into science groups so we can have sort of the right size groups, because our goal is going to be to get some slightly more sharp idea of the science requirements. We've talked a lot about that, and I would group those requirements into 4 categories maybe, and this is something we can talk about and discuss more tomorrow. But first of all, what are the measurements needed? What kind of instrumentation to address the science question you're going after? Second of all, how long do you need to observe? What is the duration of your observation? How continuous does it have to be? So the time issue. Third, the latitude. What do you get by going out of the ecliptic? How high do you need to go? To what extent do you need to hover to address your science question? And then finally, resolution. We were just talking about that, and we talked about, for example, going out to 4.5 AU, which would bring in some issues to resolution as well. I mean, so again, what does your science require in terms of resolution? So with those 4 in mind, and just to get some ideas of that, we're going to break into these groups. We'll have a rapporteur. Everybody can assign a group, somebody to take notes, and then report back after the break. And at that point, so in the morning it gets to be pie in the sky. What do you need? What are your requirements? And in the late morning then, bearing in mind what we've learned about the technology, we can start thinking about what are truly the low-hanging fruits. What are the cost benefits for these science questions? So that's kind of the idea. Just for the sake of organization, and this is in no way binding, can I see a show of hands of who, and you can float from group to group. You don't have to commit for the entire morning. And if you're doing tech, you might want to float around from one to the other. But can I see a show of hands of who is most likely to be going into the interior group? What about global connections? Great. How about heliosphere? Wow. That is kind of remarkable. I did 6, 7, 8. It was almost as evenly divided as one could hope for. So I think we can go with those categories for now and then move around in the morning. Any questions about that right now? If not, I think we're going to wind up now. So thank you all. I think the bus comes at 5:30, so you've got a little bit of time. And see you in the morning.